Welcome to Lecture 11, Analyzing Starlight, Take 2. In our last lecture, we finally started pivoting from the monumental task of introducing all of the background for the course into finally doing some real, honest astronomy or astrophysics or something approximating science that where we began the task of really squeezing information out of the light and talking about how we can do that. So today we're going to take a second step along that path and discuss in some detail about how we can use the information encoded in the light that reaches us to extract some really fundamental insights into the properties of the stars that are out there in the universe. So let's dive in. So as we finished up noting at the end of the last lecture, stars come in a number of different colors and brightnesses throughout the universe. And we ended last lecture by looking at the constellation of Orion and noting that even just within this collection of stars here, we see a number of, even just visually, we see a number of different colors stars. We see some blue stars here in Orion's belt. We see a red giant in Betelgeuse up in the shoulder. And certainly we see plenty of background color as well. And so, even without doing a detailed, very precise analysis of the stars' brightnesses, and, luminosities, and so on, we can just see with our eyes what people have known for millennia, right? Is that there's a variety of things out there, and in fact, we'll refer to that as a stellar census in a little bit, and we'll talk at great length, as a matter of fact, about how many stars of the different types are in the universe and then how they evolve and develop. For right now, though, I want to come back to something that we've talked about a couple of times already, which is this combination of distance and luminosity that affects the brightness of the stars. As we've noted a number of times, astronomy is largely an observational science, right? Because we're stuck here on Earth with the light that happens to reach us. And so one star may look much brighter than another, but when all we have to go on is what we see, that brightness, we're left not knowing, is that star bright because it's very luminous, because it's a huge star putting out huge amounts of energy, or is it bright just because it happens to be very close to us? And unfortunately, when we look up at the sky, all we see are dots of light, right? And so without something else to work on, we don't know how far those stars are. But if you remember from the last lecture, we found out that by using stereoscopic vision, by using the effect of parallax, we actually can determine the distances of relatively nearby stars to the Earth. So once we have that data point, we can disentangle the distance and the luminosity from the brightness and find both of them independently. So let's take a look at some detail. So we've talked about blackbody radiation already and drawn a number of curves and said this is what a blackbody spectrum looks like. So that wasn't all just for fun and games. I mean, it was a lot of fun, I think, but there actually was a reason for that, and the reason is that stars are blackbodies. Stars radiate very much like blackbodies, which means that everything that you learned about a blackbody spectrum and what it looks like, how it starts at zero and then it reaches some peak, which the peak of wavelength for which is given by Wien's law as a function of temperature, and then it tails off. Everything that you know about that is true of stars, right? And so, just looking at a few examples here, we're going to see, it turns out there are a lot of red stars in the universe, and those are the coolest stars. So this may seem a little counterintuitive if you're thinking about red hot, being very, very hot, and then blue being a cool color. Well, the artists, that's what they tell me, and that's fine. But in physics and in nature, red is actually cooler than blue. And that's just, it's because red photons have lower energies than blue photons. So the spectrum of a red, relatively cool star would look something like this. And, to sort of highlight the visible spectrum, I've drawn that in here explicitly. So you can see this particular red star, whose surface is 2500 Kelvin, its spectrum actually peaks just outside the visible range. So, but there's still plenty of light that is emitted in the visible range. And it appears red because you have more red photons emitted than any other color, right? So what you actually see is some combination, is the result of all of the photons, all of the light that's emitted, but there are so many more red photons emitted, so much more red light being given off that the star appears red. As you heat up to 5800 Kelvin, which you'll see a lot because it turns out that's the surface temperature of the sun, you get to a yellow star, and a yellow star peaks in the, pretty close to the yellow or the green part of the spectrum. I should say the color that we actually see, it is the result of the combination of all of these colors, but it also is complicated by the fact that the human eye is not equally sensitive to all wavelengths. So even if you had equal wavelengths or equal numbers of photons of every wavelength being emitted, your eye would not be as sensitive to all of those. Okay, so what you see is actually slightly more complicated than just what's emitted. But usually, since this isn't a biology or an anatomy class, usually we'll ignore that fact. And then finally, a very hot star, a blue star, has a peak in the also outside the visible spectrum, but now in the ultraviolet. But then plenty of visible light being given off as well here at 18,000 Kelvin. And so because there are so many more blue and purple photons being given off, the star appears blue. So at a very high level, we can see that, yeah, the temperature of the star is affecting the spectrum, is affecting the color, right? And that's going to kind of be, one of the main themes that we're going to focus on today. So on the last slide, I showed you 3 examples of colors and temperatures, but it turns out that there's a lot more than that. And so astronomers have divided stars into 7 primary spectral classes. And as you might expect, it turns out there are plenty of subdivisions within those spectral classes. And so if you go off and become a professional astronomer, you can get a whole lot more detail than this. But thankfully, for both you and me, this is going to be enough for us. And so, unfortunately, the spectral classes are named in a way that there are historical reasons for it, but despite the fact that I've told you that in general, astronomers and physicists and scientists generally are not very creative in their naming schemes, in this particular case, they were much more creative than I think anyone wishes they had been. And so there's for all practical purposes, there's no rhyme or reason to this naming scheme. It's just something that you have to remember. So on the cool end of the spectrum are these M-class stars that I mentioned on the last slide. They have surface temperatures that range between 2,500 and 3,500 Kelvin. Remember, all temperatures are in Kelvin, unless I say otherwise, which I very rarely will. The next class in increasing temperature is a K-class star, then G. For what it's worth, and I'll come back to this, the Sun is a G-class star with a surface temperature of essentially 5,800 Kelvin. And then they go on up, F, A, B, and O. So O-class stars are the hottest stars that exist. They are also the most massive, as we'll talk about. There's a very close connection between a star's mass and its temperature. And they can reach anywhere up to as hot as 50,000 Kelvin, and that's hard to do in the sense that there are very few of those. When we talk about a stellar census, we'll find out that there are a lot more M-class stars than there are O-class stars. And in general, the number, as you get hotter, the number of those stars that exist is fewer and fewer. But they are out there. And so this is the range. So, as I said, the Sun is a G-class star. And unfortunately, you are going to have to memorize these classes and the order. I'm not a huge fan of memorization in science. I think it's much more important to understand how things work rather than just to be able to regurgitate what some fool like me told you might claim that they work. But in any case, in this case, you're just going to have to memorize it, just like I had to memorize it. There is a mnemonic that may help you because the absurdity of it will help it stick, and that's "Oh, be a fine girl, kiss me." And I think I've seen that there are some different versions of this. You can use it or not use it, but otherwise, I have no idea how you're going to keep the spectral classes in order. So we're not going to do a whole lot as far as memorizing what stars are in what spectral class, for example, but we do need to know O-class stars are the hottest, M-class stars are the coolest, the sun is a G-class star, and then sort of fill in these other letters. So anyway, that's the classification system for spectral types. As I said, it's actually generally true that as we go from M-class stars to O-class stars, they get less and less common. But you can roughly break them up into two sort of groups here as well, which is that M through G-class stars are quite common. We see a lot of them out there. I've said before, and I'll say again, I'm sure, that the sun is a very sort of plain vanilla, just very normal star as far as as all the stars in the universe go. And so there are plenty of M, K, and G-class stars. As you get up to F, A, B, and O, there are fewer and fewer of those. But it's not like there's a hard dividing line anywhere in here. It really is just like we have spectra, coming from these stars. There's a spectrum of stellar types in the sense that there are some of all of these things, but as they get hotter, there tend to be fewer of them. And finally, as I said, there are plenty of subdivisions here as well. So, for example, there are G0 up through G9 and F0 up through F9, and so if you say, this 1,000 degree or this 1,000 Kelvin temperature range, that's a pretty big range. I would really like to subdivide it into 100 Kelvin sub-ranges. Well, guess what? Somebody already did that. And you're welcome to go study that further if you're so inclined. We won't be doing that. I think I will tell you the sun is a G2 star, for the record, but that's about as far as we're going to go. Now, I just made the claim that stars are black bodies, and that's why we spent some time studying blackbody radiation. But I have to caveat that now and tell you that stars are not perfect black bodies. So far what we've studied is an ideal black body that has a very nice smooth spectrum with a peak given by Wien's law again, and a total luminosity given by the Stefan Boltzmann law. But it turns out stars are a little more complicated than that. And the reason is something that I've alluded to before, but now we're going to go into a little bit more detail about, and that is that, as we'll talk about in great detail, the hottest part of a star is the core, and that as you move from the core out towards the surface of a star, you get cooler and cooler. Eventually, as you leave the star's surface, to the extent that it has a surface, right? We talk about the surface of a star, which is actually something called the photosphere, which is the opaque layer inside which you can't see. So it's not a hard cutoff, right? This is a ball of plasma held together by gravitational forces. It's not a hard sphere. But as you get outside the photosphere into the atmosphere of the star, eventually you get far enough away that it does get cool enough that stable atoms can exist, right? I've told you before, if you remember nothing else about this class, please learn and remember that stars are not made of gas, they're made of plasma, right? Within the star, it's just much too hot for stable atoms to exist, and so the electrons are stripped off by all the thermal energy, and so you have a plasma consisting of free electrons and nuclei. But eventually you get far enough away into the upper atmosphere of the star, and it does get cool enough for some stable atoms to exist. But what that means is that as the light produced by the star is moving out, trying to get out, eventually to reach us, some of those photons, some of that light is going to strike atoms in the upper atmosphere. And when it does, Some of those, if they're the right photons, if they're the right wavelengths that correspond to specific atomic transitions of those atoms, some of those will be absorbed. And so the result is that if those wavelengths are absorbed, that means that they won't get to us because they're kind of stolen by the sun's atmosphere. And so the upshot is that instead of getting a perfect blackbody spectrum, what we actually get is most of the blackbody spectrum, but with some parts, some specific lines removed. These dark absorption lines are going to be removed. And so you have a continuous spectrum that is produced by the sun, but then some specific lines are absorbed, taken out by the sun's own atmosphere. And then as a result, what we actually observe on Earth is a continuous spectrum with these absorption lines taken out. And so if we look at a G star, this is labeled G star, but I can almost guarantee with the sun, it looks like this. So we can sort of see a smooth, continuous blackbody spectrum, but then there's definitely a lot more structure there with these missing lines, these dips here. And so actually that's great news for us, because in our continuing quest to squeeze as much information out of the spectra that we get as possible, this is going to give us a wealth of information about what exactly is there in the star's atmosphere. So the first person to really put this into practice and perform a tour de force of spectral analysis was a woman by the name of Annie Jump-Cannon, who spent a very long career analyzing thousands of stars spectra at the Harvard Observatory. And she did this in the late 19th and early 20th century. She was there for a very long time and really just did a meticulous job analyzing, as I said, thousands of objects in sort of excruciating detail. And so, I've shown you a number of spectra before, blackbody spectra, and on the last slide you saw blackbody spectra kind of with the additional structure of these absorption lines. But here you see, spectra in their really full glory, and it's much more complicated than sort of the simple picture that we start with. And you can see, she went all the way from the coolest M5 stars up to the hottest O5 stars. And you can see it's very nearly continuous, right? You see there is a very nearly continuous spectrum, but obviously there is some very clear structure as well. The other thing that I would draw your attention to is just the fact that when you look at the O star, the O5 stars, and the B0 and B5 as well, obviously they have a lot more intensity in the near UV end of the spectrum. Whereas the cooler stars have much more weight, much more intensity in the red end of the spectrum. And that makes sense. That's consistent with everything that we've seen already. But it's good to see that even when you see this, very complicated and sort of full glory picture of stellar spectra, they're still consistent with the overarching sort of themes that we've discussed. But as I said, we started off with a simple picture, and that's, for this course, we're certainly not going to dive into all of the details that Annie had to go through. But it is worth seeing that to really do a complete analysis of the real world spectra that we observe, there's a whole lot of work involved, and thanks to her, she really jump-started this kind of work and led the way for a lot of people, to continue that kind of work even today. Fortunately, it's actually much easier for us now, just because we have computers now, and so this kind of process is largely it is automated today, but again, that's largely thanks to her. So as I mentioned, the sun is a G2 star, and so for what it's worth, this is kind of representative of the sun spectrum. It is very nearly 5800 Kelvin there. 5860 is written down here, and you can see it's right in the very close to the middle here. So again, I made the comment the sun is a sort of a plain vanilla star. It's right there in very near the middle of the full classification of stars. It's got a pretty uniform distribution in terms of intensity weighting. That is to say that it's got plenty of weight down here in the red, plenty of red intensity, but it's got quite a bit of violet and blue intensity as well. Kind of peaks in the middle. It's a yellow star, that's kind of nearly white, in the sense that it's got a pretty evenly distributed intensity range. Whereas again, if you look at the hottest end of the spectrum, you see almost no red light at all. But then the most of the intensity is in the near UV end of the spectrum. And of course, if we could represent it, there's quite a lot of weight even outside the visible spectrum in the UV. One thing that I do want to caution you about, though, is that the way that this particular graphic sort of represents the spectra, it does so in a normalized way, which is to say that when you look here, it looks like there's no red light at all coming out of this O5 star. In fact, there's more red light coming out of the O5 star than there is coming out of the M stars. Okay, so the number of red photons being emitted from the O5 star is actually quite a lot more than the number of red photons being emitted by an M0 star, say. But in order to sort of represent this more cleanly, the total intensity of each one of these stars is kind of normalized in such a way that they're represented the same here. And so when we look at the O spectrum, we see that there's almost no red, which just means there's so much more purple than there is red that on a relative basis you don't see it here. But it is important to keep in mind that the total intensity coming out of the O star is just phenomenally higher than anything coming out of the red star. And so there really are, quite a lot of red photons. It's just there's so many more purple photons that they're swamped. And we could go back and go through all of these as well. There's not a whole lot more detail that we need to add here. But if you've got a favorite flavor of star, or favorite classification, then you could spend your career studying it. So have at it. So to reiterate something that I've said before, our goal is, again, to squeeze as much information as we can out of the spectrum. And so the question that we need to ask is, well, what properties of the spectrum can we get information out of? And basically the answer is that we can measure the shape, the strength, and the location of these absorption lines, and use those to get a whole lot of information out of the star. So again, if you kind of squint your eyes and you lose the structure, if you ignore all of the lines, the additional structure here, you see a background of a blackbody radiation source. But as I mentioned recently, we're going to be able to use this additional structure and these missing lines, these dips in the spectrum, to figure out things about what the star is made of, what's in the star's atmosphere. And so, for example, in this particular case, we see a very strong hydrogen line here. That's not surprising because guess what? There's a lot of hydrogen in stars. In fact, that's mostly what stars are. We know it's hydrogen because we know the electronic structure of hydrogen, right? We know what the hydrogen's energy levels are. We know what wavelengths correspond to the transitions in hydrogen. So if you want to go, we can look at all the energy states in hydrogen and then say, well, what photon needs to be absorbed in order to make a particular excitation, or conversely, if the atom decays from a higher energy level to a lower energy level, how much energy would be emitted and what wavelength would that correspond to? And so this is a hydrogen line. It's one of the strongest lines here, which again is not surprising because there's more hydrogen than there is anything else. There are in fact a couple of strong hydrogen lines here. And then there's another one up at a higher wavelength. And each element has a characteristic set of absorption lines, and that's something we've talked about. It's a fingerprint, effectively, of that element. And so again, we use those. We or someone else has already done this for us, that can calculate all of the absorption lines that would correspond to a given element, and then you just start looking at a spectra and start checking them off and saying, okay, I see the hydrogen lines. Here's how strong they are, and how deep that dip goes. Here's how wide that the dip is, because you can see that they're not perfectly
It's not just a very single wavelength. It's actually it's fairly localized, but you can see it kind of dips down. It's like a steep valley, but it's not. But there is some width to that, and that actually can tell us some information as well. And we see there's a magnesium line as well. So it turns out there's some magnesium in the sun. There's some sodium in the sun. You can see those lines are not as strong as the hydrogen lines, but they're not trivial. You can certainly see them with your eye. And of course, if you put this on a computer, the computer can see things, as well that's hard for us to see, just with the naked eye. And so by doing this, we can obtain the chemical composition of the star's atmosphere. And this is exactly what Annie Jump Cannon did with, again, thousands of objects in the sky. And in fact, it's thanks to her that we discovered that stars are made of essentially hydrogen and helium with a little bit of other things. And we take that for granted now, but it turns out that was revolutionary information at the time. At the time, scientists had basically assumed that the composition of the sun and of stars generally should be the same as the composition of Earth. And that seems silly to us now, but when you don't know any better, why would you guess any different, right? What we knew was Earth. We didn't have any reason to think that the stars would be made of something different. So they just assumed, well, it's probably about the same composition as Earth. Turns out it was very different. And so when Annie Jump Cannon first published her results, there was a lot of pushback and a lot of disbelief in the results, assumptions that she just done the calculations and the experimentation wrong because the results were so different than what was expected. But it turns out she was right, and she was so right that now we just take for granted, that I think you can ask most elementary schoolers what stars are made of, and I think they'll tell you hydrogen. If not, then our school system is failing us, which is another topic that maybe we can talk about offline. So, in addition to the particular wavelengths that we can identify, again, by just, you can look up, you can go to Wikipedia, and you can find a list of the wavelengths corresponding to the electronic transition in each element. Another piece of information that's going to be useful to us is how strong or weak these lines are, by which we mean how deep is the valley in the spectrum. So down here, we see very strong lines, and that basically means there's it means exactly there's a lot of that thing. So if this is a hydrogen line, that means there's a lot of hydrogen, because a lot of the hydrogen, or a lot of this wavelength that would be there from a perfect blackbody is being taken out. Right? Not all of it is taken out, because some of that light, at that wavelength, gets through the sun's atmosphere and just happens not to hit, say the hydrogen atom, right? Only, that photon has to hit a hydrogen atom in order to be, absorbed and taken out of the spectrum. So it's not going to be completely removed, but more of it will be removed if there's more of that atom there. So we see there's a lot of hydrogen, whereas you look down here I think this was a sodium line. There's a lot less of that, right? There's a lot less sodium in the sun. There was hydrogen, so the sodium absorption line is a lot weaker. That means it's a lot smaller. And the limiting case, obviously, is if there's no, say you look at a uranium absorption line. Well, it turns out there's essentially no uranium in the sun, and so the strength of the uranium lines will be zero, right? Which is to say they're not there at all. So the less of something there is, the smaller the pullback, the smaller the valley in the spectrum, the weaker the line. And conversely, the more of something there is there, the stronger the line and the deeper that valley. So, and as I mentioned, now that we've talked about the location of these lines and the strength of those lines, another piece of information is the width of those lines. So we call them lines. Of course, a line has zero width. It's infinitely narrow. But as you can see here, in practice, that's not the case. But there's definitely variation, right? Some lines are very wide, such as down here at around 400 nanometers or so, and some are very narrow here. And it turns out that tells us some interesting information about the temperature and the pressure of the star. So a wide line means that it says gas here, but and so again, this is in the atmosphere, so there actually will be some atoms there, some plasma, some atoms. But again, if if we're going to absorb, if an atom is going to, it has to be an atom to absorb, right? If it's plasma, it can't absorb the photon. So, so a wide line means that the gas is high pressure and high temperature. So having done this analysis in excruciating detail for the sun, we now know exactly what the sun's composition is, and to greater detail than any other star, as you might imagine. And so if you're wondering, here are the results. And this table gives the percentage, gives the elemental composition both in terms of atom fraction, which is here in the first column, and then mass fraction in the second column. And the main difference here is that hydrogen is 92.5% of the sun. The sun is 92.5% hydrogen by atom number. So in other words, 92.5 atoms or nuclei out of 100 are hydrogen nuclei. But because hydrogen is the lightest element, it makes up only 74.5% of the sun's mass. Okay, so typically when I talk about the composition of a star, unless I tell you otherwise, I'm going to be talking about it in terms of atom fraction. So typically I'll say that the sun is about 92% hydrogen. But it is important to know that that's in terms of atom numbers, not mass. And sometimes it will be important to think about things in terms of mass. But you can see that there are a lot of things in the sun, but 99.9% of it by atom number is hydrogen and helium, right? So for most purposes, we can just assume it's all hydrogen and helium. And for a lot of purposes, all hydrogen. As we will find out, though, as the stars age, this composition changes, right? And that if it's a surprise now, it won't be a surprise shortly, because the stars are fueling themselves by virtue of nuclear fusion in the core, right? And so what all nuclear fusion is a process of converting lighter nuclei into heavier nuclei. So you're converting hydrogen into helium, for example, and so a star starts off almost entirely hydrogen, and then as it ages, the fraction of hydrogen drops and the fraction of helium rises, and so these will change over time. But they change, they don't change quickly on our time scales, right, in terms of a few years or decades. And so certainly for the rest of your life and your kids' lives and your grandkids' lives and so on, these numbers will be pretty darn good. So let's now think about the following situation. So let's imagine we have two identical objects which are heated to different temperatures. Okay, so these could be metal balls, they could be stars, whatever you like. But you got two identical objects that the only difference is that there are different temperatures. And so which object do you think gives off the most total light? And as usual, I'll pause here for a few seconds and let you think. And if you want more time, then pause me and then come back when you're ready. Okay, I won't pause for a whole 30 seconds here because my guess is that you picked an answer relatively quickly. So the answer, probably not surprisingly here, is that a hotter object gives off more total light, right? And this is something that we've seen before when we looked at blackbody spectra. The characteristic blackbody spectrum looks like this. It starts off at 0, it hits a peak somewhere. Where that peak is given by Wien's law, and it changes with temperature, right? The hotter an object is, the closer to the UV, the closer to the blue end of the spectrum is the peak. But also, as it gets hotter, the spectrum gets larger. Just the total intensity given off by that object is higher. And again, this is probably kind of obvious to you, but if something is relatively cool, like if it's 300 Kelvin, room temperature, or kind of like us, it's giving off electromagnetic radiation, but it's invisible, right? It's in the infrared, and the intensity is quite low. Whereas when you heat something up, in order to give off a significant amount of energy, it's got to be quite hot, right? And certainly stars, for example, when you become several thousand Kelvin, you give off a lot of radiation in the visible spectrum. But as we've seen before, you don't have to be that hot. Even if you have a burner on your stove, you have an electric stove, and you heat it up, it'll glow red hot, right? And so you don't have to be at stellar temperatures in order to give off visible radiation. But if you want to give off a lot of visible radiation, then you can do. So now let's look at the second example. Now we're going to have two objects that are at the same temperature, but one object is twice as big as the other. Okay, so which one do you think gives off the most total light? And again, I'll pause here for a few seconds. Okay, well, you probably got this one right too. It turns out the bigger object will give off more light. And the answer here is, the reason for this is just that there's more surface area on the bigger object from which to radiate. So it turns out that if I were to ask you how much radiation per square meter does each object give off, the answer will be the same, right? Each object here gives off the total amount of energy per square meter, which is just a function of temperature. So if you tell me the temperature, I can tell you exactly how much radiation per square meter is being given off. Okay, but what that means is that if they have the same temperature, these two objects, and one object is larger than the other, then the larger object is going to be radiating more energy into space. So we can summarize the observations from the last few questions by saying that an object's luminosity, which again is the total energy that it puts out per second, is affected by both its size and its temperature. And in fact, we can be a little more quantitative than that, and we can write down the following equation, which is that the luminosity is equal to the surface area of the object times what we call the flux. And the flux is just the energy per second that's radiated by each square meter of surface area. So if you tell me the flux, so the energy per second per square meter, and you tell me the surface area, which is the total number of square meters, we just multiply those together and we get the total energy radiated per second. And so in words, this is it's almost just a matter of definition by what we mean of flux and luminosity. But this is the relationship. And we can write that down in the form of an equation that looks like a little bit, well, I don't know whether you think it looks more complicated or not. It at least allows you to use a Greek letter or two. But the luminosity here for a sphere, and we're thinking about stars, which are spherical. And so we've got the luminosity on the left side of the equation is equal to the surface area, and the surface area of a sphere, again, is just 4 pi r squared, where r is the radius. And then we multiply that by the flux. And the flux here is written down as the letter J, and it's given by the Stefan-Boltzmann law, which I mentioned before, and is equal to sigma, which is just the Stefan-Boltzmann constant. It's a number that you can just look up, times the absolute temperature to the 4th power. And as I mentioned before, and we'll no doubt mention again, this 4th power is, because it's the 4th power, it's a very strong dependence on the temperature. So doubling the temperature, for example, will multiply the luminosity by 2 to the 4th, or 16. Tripling the temperature will multiply it by 3 to the 4th, or 81. And so that's why, for example, if you just double the temperature of a star from 3,500 Kelvin, which is the coolest in-class star, or close to it, you double that to 7,000 Kelvin, which is a little bit hotter than the sun's temperature. Again, you multiply the luminosity, or the total energy radiation rate, by quite a lot, again by 16 times. And so, I'll say again, this is not a class in advanced mathematics. We're not going to be doing a lot of computations, but this is sort of the summarizing equation that relates the luminosity of a star, the total energy output, to its size and to its temperature. So now let's think about the following situation. Imagine you're observing two stars, which, not very creatively, we'll label star A and star B. And star A is twice as hot as star B, while star B is 100 times more luminous than star A. And the question is, well, which star is bigger? So, and this is a situation that is actually a very realistic one, in the sense that we can tell a star's temperature by looking at its spectrum, right? If we just gather information about its spectrum following Annie Jones Cannon's example, we can compare it to Boltzmann distributions, and we can figure out what is the surface temperature of the star. So we can certainly do that. And so then the question is, okay, if we know that, and we also know that star B is 100 times more luminous than star A, which star is bigger? So I'll pause here, let you ponder for a little bit. This is one that if you want to actually do the detailed calculation, will probably take you longer than 30 seconds. So you're welcome to pause me again if you want to do that. But if you just want to kind of ponder it and scratch your chin a little bit, and then give a guess to yourself, then that's fine too. So I'll pause here briefly, and then we'll see what we can see. Okay, so I'm going to go ahead and jump forward to the next slide now and do the detailed calculation. So at least you will have seen it once in your life. So the key here is to write down the equation that we introduced on the last slide, which is probably not a surprise, but to do it for each star. All right, so we can do this twice, once for star A and once for star B. So the luminosity of star A is equal to its surface area, which is the surface area of a sphere, 4 pi RA squared, where RA is, not surprisingly, star A's radius. And then that's multiplied by the flux from star A's surface, which is given by the Stefan-Boltzmann law, just sigma T to the 4th, where that T is, again, the surface temperature of star A. And we write down an analogous equation for star B. Now, since the question is asking us about the relative size of the stars, which star is bigger, what we're interested in calculating is the ratio of the radii, RB over RA. And so to get that, what we're going to do is first divide the luminosities. And so if we divide LB by LA, we get the following expression, which we can simplify a fair amount by canceling out the factors of 4 pi and canceling out the Stefan-Boltzmann constant. And if we then group terms a little bit, we find out the ratio of the luminosities is equal to the ratio of the radii squared times the ratio of the temperatures to the 4th power. Okay. And now the only step that's left is to solve this for the ratio of the radii, because that's what the question is really asking us for. So just two more algebraic steps, right? And if you're interested in the algebra, I can talk to you, happy to talk to you in detail about that. But the result of that is that the ratio of the radii is just equal to the square root of the ratio of the luminosities times the ratio of the temperatures, inverted, to the 2nd power. And so just plugging in the numbers then, we've stated at the outset that star B is 100 times more luminous than star A. So we have the square root of 100 here, and TA is twice TB, so we have a factor of 2 here. Do the math, and we find out that RB over RA is 40. And so we've answered the question, and star B is 40 times as large as star A in radius, right? In volume, it would be 40 to the 3rd power times larger, so it's much, much larger in terms of the volume. It's 40 times as large in terms of the radius. And so that's the answer. And that brings us to the end of the lecture. So I appreciate your attention as always. Thanks for sticking with it. I hope that you've learned a little bit more about how we can extract ever more information out of stellar spectra. And I hope that you'll tune in for the next lecture, lecture 12, as we continue the saga. So until then, enjoy.